So today we're going to be looking at the limits of summation. We've gone over a few different sections where we've tried to find the area beneath a curve, either by bounding it with right and left endpoints, which gives us a general area that the area is between, or by taking an estimate of the midpoints, which doesn't give us an area, but it gives us something in the neighborhood of where that value is supposed to be at. Both of them have their pros, both of them have their cons. This is a little bit more advanced to figure out. It takes a few more steps in the middle. These are pretty basic to do. Now, one of the questions you might have asked was, we've noticed that as the number of rectangles increases, our estimations get better. In the beginning, when we were doing 4 or 5 rectangles, we were getting some big areas. Our left and right endpoints left a large gap. Later on, when we did midpoints, we noticed that we were within 1 or 2 values of the actual answer, but that's not necessarily a guarantee. So let's crank up the number of rectangles, theoretically, to infinity. What do you think will happen if we have an infinite amount of rectangles? Well, as we take a short aside, we know that we're summing the base times the height. And we know that if we're looking at the number of triangles from 1 to infinity of any type of value, something's going to happen to our base. We know the base is going to be wherever the endpoint is, so let's say b minus a all over n, and if n is infinity, that is going to be b minus a over infinity. That's going to reduce down to 0. And so in essence, what would happen is if we take our summation notation, we are finding the sum of 0 times whatever the height is. And so we're going to say the function of one of the points, either mid, left, or right. And if we take the summation of 0 times anything, we know that that completely cancels out our process. However, if we look at it from a head-on perspective, yes, we will have a reduced down to 0, but when we plug in our infinity, we'll have infinities over in this aspect. So today what we're going to be focusing on is what happens when we actually evaluate n to be infinity. It looks like it should be 0, but it'll play out to something a little different. So the first process that we have is we have to pick which formula to use. We know left and right endpoints weren't exactly good. Some were over, some were under. The midpoints were a little better. But the question that we're going to ask, secondly, is does it matter which one of these formulas to use if we're using an infinite amount of rectangles? If your answer was it doesn't matter, then yes, you are correct. So I'm going to look at these 3 formulas and say which one looks the easiest to do. You're probably going to pick the right endpoints. Because again, if we're using an infinite amount, it doesn't matter if I'm going above or below, I'm getting really, really close. Midpoints, again, I'm getting really, really close. So I'm going to use the simplest to figure out. So let's go ahead and take a look at number 1. Now, number 1 has an overall area of 5,333.3 roughly. So I'm expecting to get that number. Okay. So again, we notice that with our values right here, I'm going to figure out what my delta x is. My delta x is going to be 20 minus 0 all over n. And we know that as n is approaching infinity, we're going to eventually plug that in, but we're going to hold off just now. And we're going to say, actually, it's going to be 20 over n. We'll plug in what comes later. And so now that we know that, let's go ahead and figure out what this general formula looks like. Now, the first thing that we have to get used to is we're dealing with a limit here. So I'm going to say this is the limit as n is approaching infinity of our summation of I equals 1 to n. Remember, the number of triangles, or the number of rectangles that we're doing is going to approach infinity, of our regular old base times height. And now what we're going to be simplifying here in the first few steps is what is this part? I'm just going to drag down the limit and drag down the summation notation as we simplify what would go in here. Okay, so we know our base is just going to be our delta x. So our delta x in this case is going to be a 20 over n. The part that we have to evaluate, and let's do this in a different color, let's do this in green, is going to be our function. And now we have picked the simplest formula to plug in, a plus delta xi. In this case, our a is 0, so it's just going to be delta xi. There's no adding or subtracting, nothing weird going on here. So we're going to say f of, I drew another f there, a plus delta xi. So f of our a is going to be 0, our delta x is 20 over n, I. Cool. So if I simplify that, I'm literally just going to get f of 20i over n. I'm plugging that into my general equation. And I'm keeping the 20 over n over here. Okay. So when we plug that into our equation is 2x squared. So I'm going to say it's 2 times that squared. Okay. So now this part is the part where we did the calculus process. The rest of this is just going to be algebra. We're going to be simplifying this as best we can so that we can then take the summation and then take the limit. But this is the calculus aspect. What are we doing? How are we doing it? So now let's crank out some algebra here. I'm going to go ahead and, at this point, let's switch over to, now we're going to keep it in green and black until we combine the two. So with my green aspect, I'm going to square this. So that's going to become 2 times, that's going to be 400 I squared over n squared. If I distribute that 2 in there, I now have 800 I squared n squared. And this is where I'm going to change my color. So 20 over n, 20 over n. And then when I combine these two, let's see. 20 times 800 is going to be 2 times 8 is 16 with 3 zeros. So 16, 0, 0, 0, I squared over n cubed. And at this point, I'm going to drag these down. So these theoretically should have been written all the way. I'm just going to save it till the very end. Summation of I equals 1 to n of the limit as n approaches infinity. Boom. So this is the part that we're going to focus on. So I'm going to do a little half box because that's an important piece. For our next step, we're going to come up here. And I'm going to continue this on. But I'm going to separate this into the summation aspects. So I still have the limit. I have not addressed the limit yet. So the limit as n approaches infinity of this. And now I will pull the constants out. So I have 16,000 over n cubed of the summation from I equals 1 to n of I squared. Perfect. Now this we know how to rewrite. This is just the summation rule. Let's go ahead and copy this down. So I have 16,000 divided by n cubed. We know the formula for this. Normally we would plug in a value for n, but seeing as this is just a generic n, we don't need to plug in anything. So it's going to be n times n plus 1 times 2n plus 1 all over 6. And again, we haven't addressed the limit, so we're going to drag that down until we actually plug in the limit portion of this. But now that we've addressed the summation portion, again, let's bust out some algebra and simplify this as best we can. I notice the first thing is that some of these n's are going to cancel out. That n disappears because I have an n cubed on the bottom, which will now just be an n squared. The 16,000 and the 6 are both divisible by 2. I'm going to go ahead and divide those, just to make my numbers a little easier. So that's going to become an 8,000. And that's going to be a 3. Cool. So I'm going to copy these down, and then in the next step, I'm also going to FOIL this. So let's see, as of right now, I have 8,000. I have n squared in 3, so 3n squared. And I'm going to go ahead and I'm going to FOIL this right here. This is going to give me 2n squared. I have plus 2n plus 1n for a total of plus 3n. And then 1 times 1 is going to give me 1. So far, so good. Lastly, I'm going to distribute this 8,000 into all three of these. So that's going to bring me back to a 16,000 n squared. That's going to be a 24,000 n and 8,000, all divided by 3n squared. Okay, so now at this point, you should recognize the shape of this graph, and the shape of this graph is going to be a rational function. I have n squared and n squared. We know that we can abbreviate this whole process by the horizontal asymptote rules that we've covered. Now, the horizontal asymptote rules is that the endpoint, as we approach infinity of the shape of this graph, is going to approach the ratio of the largest power of their coefficients. So my n squareds I have a 16,000 and a 3. I know the horizontal asymptote, let's come over here to the side and do this in orange. So my horizontal asymptote, let's call this my HA, or actually I'll just write it out. Is that y is approaching 16,000 over 3 as x is approaching infinity, which is exactly the same setup as what we're looking at right here. Y is going to be approaching this value. Our area is going to be approaching this value as n, which is in the place of normally where our x would be, approaches infinity. Now, we could quote that rule, but again, when we're dealing with a limit and we're dealing with this style problem, we're going to tend to want to show our work as to how we got to that. But I bet you 16,000 divided by 3 is going to be that right there. But as an aside, just know that we've seen the shape of this particular graph before, and we can take that shortcut if we're pressed for time. But let's actually break down where we get that from. So the first thing that I'm going to do is I'm going to break this into 3 pieces. So if I plugged in infinity right now, I'd have infinity plus infinity divided by infinity. Infinity over infinity is indeterminate. I can't do anything with it. So let's break it up into 1, 2, 3 portions. So I'll take 16,000 n squared over 3 n squared. Then I'm going to take 24,000 n over 3n squared, and then plus 8,000 divided by 3n squared. Now this is the last part where I would actually have my limit notation. So the limit as n approaches infinity is technically written every term all the way down to there. And then at this point, we can do a little bit of reduction and plug this in. Actually, it might be clearer if we just go ahead and reduce it and show you what it would look like. Both my n squareds cancel out. One of those cancels out, leaving me with just an n, and none of those do. So let's actually plug in our infinity into what we have left. So at this point, I have 16,000 divided by 3 plus 24,000 divided by 3 times infinity. And then I have 8,000 divided by 3 times infinity squared. So boom. Right here, I no longer have the limit notation because I have actually plugged in the limit. I have actually entered in n equals infinity, so I don't need to write the limit anymore. At this point and all down these, I haven't actually plugged it in, so I need to keep writing it. Notice we wrote the summation notation all the way down until we actually abbreviated the summation notation, and then we no longer wrote that sum prefix. At this point, we're going to ask ourselves, okay, what would this evaluate out to? 16,000 divided by 3, we can compute that. The 24,000 divided by 3 times infinity, well, 3 times infinity is infinity, and anything divided by infinity is 0. So this whole thing cancels out to 0. Same thing over here. This is infinity squared, so this is a larger infinity, but it's still any finite value divided by infinity is going to be 0. So I have 16,000 divided by 3 plus 0 plus 0. So actually, let's write that. Whoop. Plus 0 plus 0. And if I take 16,000 divided by 3, we get 5,333.3 repeating. And this is the actual area. Boom. And so the process itself, if we take a step back and look at this, isn't too complex. There's a lot of algebra going on here where I'm rearranging terms. But for the most part, it's pretty straightforward. I plug in these two things, simplify it as best I can. Once I simplify it, I use the summation notation and then simplify it again. Once I've simplified it again to this point, I'm going to take a note saying, hey, I can't have infinities on top and bottom, but if I split it into 3 distinct pieces, boom, it doesn't matter because I'll only have infinities on the bottom over here. I won't have anything going on weird with this first term. And then I can evaluate what it goes out to. Perfect. So now that we've done one like that, let's do one that's going to have a little bit more, I guess you would say, chaos in the middle. Let's jump off to this one. Now, as a heads up, there is not enough space in this, so we are going to be abbreviating our work on a separate sheet right here, just to give us some more room. So let's go ahead and state that this is going to be the work for number 3. We have the function 2x squared minus 1/2 x, so I'm looking at a quadratic. I'm only looking at it from 1 to 5, so it's not a relatively big area, but again, I'm looking at hitting this exact number. So I'm going to go through the process of figuring out what I need to do. So the first thing is, let's find out what delta x is. Now delta x is 5 minus 1 all over n, so 4 over n. I don't know how many rectangles there are, but again, we're going to approach infinity. So our value is going to be the limit as n approaches infinity of the number, the sum of all the rectangles inside this curve from the first one to the last one. The last one is going to be the infinite last one of base times height. And so let's spend a few minutes going through this right here. So our base times our height. I don't know why the camera's having problems focusing right now, but let's just go with it. Delta x is 4 over n. Our height over here is going to be the function, and I'm going to use the right-handed rule, a plus delta xi, as simple as possible, which is going to give me our starting point is going to be 1 plus delta x is 4 over n I. I can't simplify this really any further, so I'm just going to go ahead and jump straight into this and say, okay, this is going to be 2 times that squared minus 1/2 times that. I'm plugging in a 1 plus 4i over n. I'm moving the I into the numerator just to write it a little more abbreviated. 4i over n. So we get that. Okay. And so now I'm going to be simplifying what's over here on the left so that I can eventually distribute this 4 over n into that. So the first thing to do is to square this. So I'm going to square the first, which is going to give me a 1. 1 times 4i over n is going to be 4i over n. Double it. 8i over n. And then 4i over n squared is going to be 16i squared over n squared. I'm also going to distribute this 1/2 into there. So minus 1/2. Let's see, that's going to, 4 divided by 2 is going to be 2, so minus 2i over n. Or I could put 4i over 2n, which I would then later reduce, but there we go. We have that. Next, I'm going to distribute this 2 into there so that I can start combining these things with unlike denominators. So that's going to be a 2 plus 16i over n plus 32i squared over n squared minus 1/2 minus 2i over n. Okay, so now we have a little bit of combinations to do. The first thing that we want to do is we want to combine anything that is over an n. Actually, hold on. We're going to want to try and combine these into our I squareds and our i's. So I have no other I squareds, so I'm going to try and combine these guys. And separately, I want to try and combine my constants. Cool. So let's see. So 2 minus 1/2 is going to be 3/2. Let's see, then I'm going to combine those. So 16i over n minus 2i over n is 14i over n. And then I have this 32i squared over n squared. Okay. Now, my function has been simplified as best I can. Now I'm going to plug in this value. So now I'm going to convert this over to black because we're combining the two. So that's going to be 12 over 2n. Let's see, 14 times 4, that's going to be 40. 56i over n squared. And this is going to be 32 times 4, that's 120 plus 8, 128 I squared over n cubed. Awesome. And now this is the point where I'm going to separate it into my summation aspects and split it off. So I have the summation from the first rectangle to the last rectangle, and I'm finding the limit as those number of rectangles approaches infinity. So this is the point where I'm going to want to come over here and start getting rid of the summation aspects. And again, we should have been writing these all along, but to save on space, we're just going to do this. Okay. So now let's split this up. I'm in a new column, so I'm going to rewrite the notations that I need to include. The limit as the number of rectangles approaches infinity. I'm going to start breaking these out. Okay. So this one doesn't have an I, so I'm going to say the limit of the sum, I equals 1 to the last one, of 12 over 2n. I should have just written that as 6 over n, but yeah. And then we're going to say, I'm going to move the constants out to the front. I'm going to leave the I in there. So plus 56 over n squared times the sum from the first rectangle to the last rectangle of I. Again, I'm going to move my constants out to the front. So plus 128 over n cubed of the first rectangle to the last rectangle of I squared. Okay. Now we're going to simplify this. So I'm going to leave the limit because I haven't evaluated that, but I'm quickly going to drop the summation notation because I'm plugging those values in. So right here I have I'm going to write this now as a 6 over n because 12 divided by 2 is going to give me that, plus 56 over n squared, plus 128 over n cubed. And when there's no changing value, I'm just going to go ahead, I'm going to multiply by n. When it's the summation of I, this is going to be n times n plus 1 all over 2. And I squared is going to be the sum of n times n plus 1 times 2n plus 1 all over 6. Cool. And now we're going to simplify these in the same way that we did previously. We're going to combine them all together, hopefully into one simplified fraction. So let's do it. The n's cancel out. I'm left with a 6. Cancels out. These n's cancel out. I'm left with an n down there. These n's cancel out. I'm left with an n squared. 56 does divide by 2. That's going to give me a, let's see, 25 plus 3 is 28. It's a 1. Same thing right here. This divides by 2. That's going to be a 64, and this is going to be a 3. Okay. So 28 times n is going to be 28n. 28 times 1 is 28. And on the bottom, I just have n. Okay, so over here I have 64. I'm going to go ahead and FOIL this. I have 2n squared plus 2n plus n is plus 3n plus 1, all divided by 3n squared. So when we look at this, we see again that we're going to be approaching these n squareds. These are going to take precedent. We could use the horizontal asymptote, but we're going to work it all the way through. Okay. So the first thing is I'm going to distribute the 64 into there. So 6 plus 28n plus 28. Let's see, that's going to be 128n squared. That's going to be 180 plus 12. Okay, so I have fraction 1, 2, and 3. I'm going to combine them together by finding a common denominator. That common denominator is going to be 3n squared. So I need to multiply top and bottom by 3n to make it a 3n squared. So 3n. Top and bottom over here, I'm going to multiply by 3n squared. This will make them all under a common denominator of 3n squared. See, 28 times 3, that's going to be 60 plus 24, 84n squared. Boom. We have them over one large fraction, and now we're going to go through and we're going to do what we did previously. And we're going to combine the terms that we can. Let's see, n squareds. I have 3 of them. And then single n's, I have 2 of them. So if I copy down the n squareds, 18 plus 84 is going to be 94. That's going to be 102. 102 is going to be, let's see, 102 would make that 130, 230. '84 plus 192. Let's see, that 4 is going to make that 196. Plus 19, that's going to be 276. Okay. And we're going to have to scroll down just a little bit as we complete this simplification process. Now I'm going to split it into 3 parts. So 230n squared over 3n squared plus 276n 3n squared plus 64 over 3n squared. Now, one of the questions you might ask was, hold on, didn't we go through all of this to take these 3 different pieces? First off, didn't we take all this to move this into 1? We split it up into 3 to move it back into 1, and now we split it back into 3. The answer would be we're moving through, in essence, gates. We know that to find the summation, we can find the summation of this whole thing, but it will take an infinite amount of time as it currently sits. If I split it into 3 pieces where I have the summation of I and I squared, I can move through this gate quickly using a formula. n times n plus 1 over 2, n times n plus 1 times 2n plus 1 all over 6. And I've passed through that gate in the 3 separate pieces. Now I've got n squareds all over the place, n's all over the place, and constants. I want to combine them for my next step to move through this gate. So once I combine them, I see the fact that I can remove some of these things together so that I can then take the limit. In this case, these cancel out. This turns into an n, and that doesn't. And this is the last step where we have the limit notation written out. After this, we're going to actually plug in infinity. So at this stage, when we plug in the infinity, I no longer need to write the script. So this becomes 230 over 3 plus 276 over 3 times infinity plus 64 over 3 times infinity squared. Awesome. And so when we look at that, we notice that anything divided by infinity leads to 0. Anything divided by a larger infinity also leads to 0. So realistically, what I'm looking at is 230 divided by 3 plus 0 plus 0. And 230 divided by 3 gives us the actual area of 76.6 repeating, which is exactly what we were hoping to find right here. We know that the estimated area is 76.7 roughly. 76.6 repeating is rounded to that value. Perfect. So this process, albeit was a little longer in the simplifying step, didn't really take any new steps. We know it's still base times height. We still plug it in and simplify it so that we can split this up into 3 pieces and simplify it. And at the very end, this is the only new piece. We're plugging the infinities where we can. Boom. So now that we've seen number 3, what I want you to do is I want you to pause the video and I want you to try out number 5 on your own. Pause the video, unpause it when you're done, and see how well you did. Okay. So now that you've had a chance, what we're going to do is we're going to continue this process on, again, this is not a large enough box, on a separate sheet of paper. Pop our paper down. And let's approach number 5. Okay. So our first step is we're looking at this formula and we notice that our original function is not simplified. That shouldn't be too big of an issue. We're just going to go ahead and FOIL this and distribute that in there, but that doesn't stop us from saying, what is delta x? Well, delta x is from 12 to 4. We're splitting it up n times, which is 8 over n, and we're going to quickly approach infinity with our n's. Okay. Now, the first step that we're going to do is we're going to say, hey, what's going on with this? I'm going to take 1/5, and I'm going to go ahead and I'm going to FOIL this. So 3x times x is going to give us a 3x squared. We have a minus 5x plus 6x minus 10. Should be the 1/5. This is 3/5 x squared plus 1/5 x minus 2. So this is actually the formula we're plugging in. So this makes our life a little easier because now I know that that's where I'm going to plug in my 8 over n. So let's get to hopping. I have my limit as the number of rectangles approaches infinity of the sum of all of those rectangles from the first rectangle to the last rectangle of base times height. And I'm going to be simplifying what this is right here. My base, we know, is going to be 8 over n. It's going to be delta x, which we know is going to be 8 over n. My height is going to be the function of it's going to be the function evaluated at each point. We're going to use the right endpoints of a plus delta xi, which means that we are going to plug in our starting point of 4 plus 8 over n I. Cool. So our function, as we evaluated, is going to be 3/5 that number squared plus 1/5 that number minus 2. I'm going to go ahead and move the I up into the numerator. Actually, let's zoom in just a little bit. Moving my I up into my numerator so that it's an easier process. And then let's go ahead and start simplifying what's in the function. Okay, so right here we're going to get this squared, so 3/5 times 16. 4 times 8 is going to be 32. 32 times 2 is 64i over n. And square the last is going to be 64i squared over n squared. Should be my 1/5 into that. And I get, it is plus 1/5, yes. Plus 4/5 plus 8i over 5n minus 2. So the process is looking any different. It is a little bit longer, so I'm assuming it's going to take a few more steps to simplify this, but the process is no more difficult than what it was before. Okay, and then I'm going to distribute my 3/5 into this. Let's see, 3 times 16 is going to give us 48 over 5. 3 times 64. Unfortunately, at this point, I am going to have to break out the calculator because my arithmetic skills are getting a little exhausted here. 64 times 3 is 192. 5n plus 192i squared over 5n squared plus 4/5 plus 8i over 5n minus 2. Okay. I want to do what I can to combine my terms. I know I have an I here and an I here. And then I know I have some constants that I'm going to have to combine of constant, constant, constant. So we see that 48/5 plus 4/5 minus 2, that's going to make it 52/5 minus 10/5 is going to make that 42/5. The 192 plus 8, both over 5n, is going to give us a 200 over 5, which is going to reduce. And then we're going to have that left over plus 192. In fact, let's inscribe that a little more clearly. Plus 192. Now at this point, we can go ahead and we can start combining. You may want to reduce this one step further before we continue, just to make sure we have things as reduced as possible. But we notice that we're probably going to have to get rid of some things here in just a moment. So let's scratch that and just work our way all the way in. So 8 times 42, that's going to give us, let's see, 8 times 42 is going to give us 336. So we have 336 over 5n. 8 times 200 is going to give us 1600 I over 5n. plus 8 times 192 is going to give us 1536. I squared over 5n cubed. Actually, that's going to be a 5n squared right there. So we have this, and then this is going to be the final aspect. And just because we did put one green bracket, we don't need both of them because we just distributed that in there. This is going to be the last term where we have our summation notation included. So what we're going to do is we're going to cover ourselves and say, hey, the summation notation was included all the way down to right here, from when we were summing the first rectangle to the last rectangle. And we are going to take the limit as the number of rectangles reaches infinity. Now this is going to be the last step before we start getting rid of the summation notation. We will still have the limit because that is the last thing that we're going to be able to apply. So as we come over here to the right, let's go ahead and rewrite our limit as n approaches infinity of this. Whoop. Okay. The first one is a constant. I don't see an I, which means we're not really counting the rectangles in this one. So I'm just going to go ahead and put the sum of 336 over 5n. We're going to take this and say, we're going to pull out the coefficient of 1600 over 5n squared, and we're going to leave the I in there, because what that's going to do is that's going to allow us to sum the I. And we're going to pull out the next coefficient right here and say plus 1536 over 5n cubed. Sum of I squared from the first to the last rectangle on each one of these. And so what we see is that we have 3 of them. We're going to go ahead and we're going to start sectioning these off. So I have 336 over 5n times n. I have 1600 divided by 5n squared times n plus 1, all divided by 2. And then the last thing that we're going to be doing, as we zoom in right here, is plus 1536 over 5n cubed times n plus 1, 2n plus 1, all divided by 6. Okay. We're going to start eliminating some of these. I'm going to get rid of, well, now one of the things that we're going to notice is that I'm going to get rid of the n right here, and I'm left with n squared. And I'm going to try and reduce some of these. So like 1536, we're going to check to see if that is divisible by 6. 1536. And yes, that is. We'll get 256 over 1. So as of right now, the denominator is 5n squared. I have a 5n squared, so I'm really only going to get rid of the 2. So that way I have 5n squared, 5n squared. Right now I have 5n. So as opposed to canceling those out, what I'm going to do is I'm going to multiply times another n. That way I have 5n squared on the bottom right there. So I have 336 n squared plus, in this case, let's see, I have 800n times this. That's going to give me 800 n squared plus 800 n plus 256, and then I'm going to FOIL this, so 2n squared plus 3n plus 1. And now what I'm noticing is that because they're all over 5n squared, I can just go ahead 5n squared, 5n squared, 5n squared. I can now just look at their coefficients and combine them. But really the last step before I do that is distribute that 256. And let's see, 256 times 2 is going to be 512. And then 256 times 3 is going to be 768. All over the common 5n squared. Okay. Now at this point is where we start combining them together. Let's see, I have my n squareds. We also have our n right there and right there. Let's go ahead and combine these. So we got 336 plus 800 plus 512 is going to give us 1648. And then we have 800 plus 768 is going to give us 1568. And then we have 256 over there. Okay. This is going to bring us to the stage where we split it up into 3 pieces. Now that we've combined all our terms, now we can split it back up, similar to the way it was before, into our individual terms, but we knew that some of these terms were going to match up, so we had to push them all together so that when we pull them apart, the individual terms were good. Okay. So let's go ahead and reduce what we can. That reduces down to an n and nothing over there. And now this is the last stage before we put the limit. So I'm going to make sure that my limit notation is included all the way down. So everything from up here has included a limit notation, and that's the last one that doesn't. So now what I can do is I can go ahead and rewrite this with the limit plugged in. Over 5 times the limit that we've plugged in is infinity. We're adding 256 over 5 times that limit that we just plugged in, infinity squared. And we know that anything divided by infinity is going to reduce down to 0. Same over here. I've just got a bigger infinity. So really what we're asking is, what is 1648 divided by 5 plus 0 plus 0? So let's see what we get for our final answer. So we get 1648 divided by 5, and we get 329.6. And this is the absolute, or the exact, area. Boom. And we know 329.6 does match with our expected 329.6. So there is 0 rounding. We found the exact area beneath that curve. And there you go.